This video is on the effective nuclear charge and periodic trends. So we can remember back, we talked about Bohr's description of the hydrogen atom, and we looked at the different energy levels of electrons in the hydrogen atom. We used Bohr's equation, where we were able to find the energy required to excite an electron at different energy levels, where Z was the nuclear charge and N was the integer orbital level. This worked great for one electron systems, such as hydrogen, helium +1, or lithium +2. So we used it to predict perfectly the hydrogen atomic emission spectrum. But what about for atoms with more than one electron? What is the effective nuclear charge then? Well, effective nuclear charge is the attraction a particular electron feels for a more positively charged nucleus, considering orbital placement and other electron repulsion. So if we were to look at sodium in a simplified system, sodium has a nucleus, and in that nucleus there are 11 protons, each with that positive charge. Next we have 10 core electrons in the 1s2, 2s2, 2p6 locations, and then we have one lone electron in our 3s orbital way out here. This electron out here is shielded by the core electrons. So if we were to get rid of the core electrons, we could simplify to see that we have this effective nuclear charge of 11 protons trying to pull on this one electron super far away. These previous electrons shield our outer electrons, so these core electrons shield this outer electron, and so the energy of the last electron is its attraction to the atom. To calculate the effective nuclear charge, we need to know its ionization energy. Ionization energy is the energy required to move an electron from a gaseous atom given in kilojoules per mole. So we can have the first ionization energy, second ionization energy, etc. We can manipulate Bohr's equation by figuring out our particles per mole to just get us in to joules. So to do that, I multiply my negative 2.178 times my 6.02 times 10 to the 23rd, and I get 1.31 times 10 to the 6 joules per mole, again multiplied by my z squared over n squared. This comes out to being 1,310 kilojoules per mole, z squared over n squared, and from there I can solve for my effective nuclear charge. I can use this equation, knowing ionization energies of electrons, to figure out the effective nuclear charge of my atom that I'm looking at. So based off of orbital shapes, the s electrons are going to penetrate more than p, d, or f electrons. Due to the penetrating effects, simpler shapes have lower energies and fill in that order. Thus, orbitals fill s before p, before d, before f. So if we were to look at some graphs about where electrons would be in the s orbital, we would notice that if the center is my nucleus, my electrons are going to be fairly close to the nucleus here. From there, if I look at my p orbital, I can, this is on a plane, a 3D plane, so I have my x, my y, and my z. So I'm looking at my 3D plane, I have my p orbitals that go along my x-axis, so px, my p orbitals that go along my y-axis, py, and my p orbitals that go along my z-axis, pz. And these are just a little bit further. They're less energy, or the electrons are less likely to be here at the center. In fact, the probability is almost 0. Whereas my probability in my s electrons are fairly high that it could be at the center. Then my d orbitals get a little bit more complicated. I have dxz, where I have 4 lobes on my xz plane. I have dyz, where I have 4 lobes on my yz plane. I have dxy, where I have 4 lobes on my xy plane. And then I have dx squared minus y squared, which are the lobes in the areas in between the planes. Finally, I have dz squared, which is where I have this circular region, it's kind of like a ring, where there's no probability in the center. Then I have this large lobe on the top and large lobe on the bottom. But we can see again here, my probabilities are further out. I have more probabilities to be further outside than inside and in different locations along the outside, so further away from my nucleus, than I do in my s. And then f orbital is even more complex. There's 7 different orientations of that one. And you can look up these diagrams online, or they're also in your textbook. But you can see what's illustrated here is that s orbitals are very simple. Therefore, there's lower energies in order to fill in that order, so their electrons are going to come here first. But then if I try to remove an electron from here, it has a very strong pull on the nucleus because it's so close to the nucleus with all those protons there. So it's going to require a lot of energy to pull it off. Now, our periodic trends, there's a couple that we're going to look at. The first one is ionization energy. This is the energy required to remove an electron from an atom. If I were to look here at aluminum, going from aluminum atom to its first ion, which is the +1, the ionization energy to remove this electron, which is this guy here, is 580 kilojoules per mole. To remove my next one, my second one here, it's 1,815. And then my third one is only 27.4. That's because aluminum would rather lose all three and lose this one here and have a full outer shell than to keep this guy. So it has a little less of a ionization energy required to remove this electron. But then if I wanted to remove one of my inner electrons, so like this guy right here, my atom would put up a huge fight. It does not want that electron to get removed. It's a core electron. And so all of a sudden my ionization energy jumps up to 11,600 kilojoules. So the fourth ionization energy requires a core electron to be removed, which it really doesn't want to do. It's close to that nuclear charge. It has less shielding going on. There's only 2 electrons to shield it as opposed to 8 and 2 being 10 total. Whereas my first 3 electrons removed were valence electrons. They were happy to get out of there. There wasn't much charge pulled on them from the nucleus. So if I'm looking as I go across the periodic table, my ionization energy is going to increase. This is because as I go across the periodic table, I'm putting more electrons into the same principal energy level, and those electrons in the same level do not shield effectively, nor do they feel a greater effective charge. So that would be like if we were in here and I was just adding more electrons to my ring, I'm not going to be adding more to my I'm not going to be increasing my effective nuclear charge very much as I go across. However, as I go down the periodic table, my ionization energy decreases. This is because as we go down a group of the periodic table, the last electron is added further away from the nucleus, and that electron doesn't feel that effective nuclear charge because we've added a whole nother ring on the outside. We've added an entire energy level, so we've added it much further away from the nucleus, whereas these ones are all on the same ring. So if we were to look at a graph of our first ionization energy, we can notice as we go across a group, here we have beryllium, carbon, nitrogen, fluorine, neon. Across the group, their ionization energy increases. Sorry, across the period, the ionization energy increases. As I go down my groups, I can see that my ionization energy decreases because these electrons are further away. There's a couple of abnormalities, such as here from beryllium to boron. We have a decrease here because the 2s electrons are going to shield that first p electron that I put in. So there's a little bit of shielding going on, thus the energy is going to drop. And then similarly, but a little different here, nitrogen drops from nitrogen to oxygen. And this is because now my 4th electron there is going to enter a half-filled orbital. So that orbital right now has the line and it has 1 electron in it, and then I go ahead and add another electron in there. There's a little bit of repulsion between the 2 electrons, and that's going to spread them a little further apart, and that's why we don't need as much energy there. Electron affinity is another trend on the periodic table. It's the energy change associated with the addition of an electron to a gaseous atom. So as we go across the periodic table, electron affinity is going to increase. There's a lack of shielding by electrons in the same level. This causes the effective nuclear charge to increase, going left to right, and therefore more energy is released, so the charge is greater. As we go down a group, the electron affinity decreases. We're adding electrons further away from the nucleus, which causes a need for less energy for an electron to be released. So across increases, down decreases, the same pattern that we see for ionization energy. When we look at the graph for electron affinity, we notice that there's a few more exceptions to the trend than there was for ionization energy. We can still see our trend illustrated as we go across a group. I have lithium, boron, nitrogen, and neon, and it does increase. I can see as I go down a group, I have lithium, sodium, potassium. It does slightly decrease, but not nearly as much as it did back on our ionization energy. So we look at some of the abnormalities here, some of those exceptions. So going from carbon to nitrogen to oxygen, why does it go up and then back down? Well, when we're adding electrons to the carbon, it enters an unpaired p orbital. However, when adding electrons to the nitrogen, it enters an occupied p orbital. And the difference between unoccupied and occupied, we have some of that repulsion going on, and that's going to affect whether or not we have an increase or a decrease in electron affinity. Finally, we have atomic radius. This is the side of the atom. We can't know it directly because we cannot see electrons because they're not stationary. However, we can figure it out by the distance between orbitals, and we can measure that. As we go across a period, atomic radius decreases. This is because there's poor shielding from the inner electrons. Thus, the radius decreases. So we talked about how our electrons get held on tighter as we go across the period, and that means that that nuclear charge is going to pull on those outermost electrons and pull them in closer. So as I add in a proton, it pulls on those electrons and it pulls them in. It gets greedy as it goes across. It wants to hold on to those electrons tighter and tighter and tighter. However, when I go down a group, my atomic radius increases because as I move down, electrons are added to higher energy levels, and there's more electrons needed to occupy more space. So I'm adding rings as I go down the periodic table, so my atom gets bigger and bigger and bigger. We can see that in our table here. It illustrates my atomic radius of my different atoms. We can see we have hydrogen here with a radius of 37, I believe these are picometers. And then helium has 32. This is the smallest atom on our periodic table. We notice that as we go down our groups, they're getting bigger because I'm adding energy levels. But still, as I go across, they're going to decrease. So in this case, cesium is my largest atom. If you think of the periodic table as helium having this extreme smallness in the upper right, and cesium or francium having the largest atoms in the lower left, all of our other trends are based off of the size. So where those electrons are in regards to, or in relation to where the nucleus is and the charge of the nucleus. If they're really close, it's going to require a lot of energy to get rid of them. If they're really far away, it's very easy to pluck them off. And so based on these two extremes, we can then figure out or rationalize our other trends.